Well, what did we do last week? We worked with triangles, special triangles. Today we're going to move on, work with quadrilaterals and circles. Mostly what we're going to do is look at applied problems today. We're going to solve some applied problems involving quadrilaterals and a few involving circles. So, some of what we're going to do today is likely to be a review. Some of it will be a brush up, some of it will be a review. So, what is a quadrilateral? Four sides. That's right. Quadrilateral is any polygon that has four sides. That is review. That's good. Now, there's several different types of quadrilaterals, including the square, the rectangle, the parallelogram, the trapezoid, and the rhombus, which I don't have listed there. But we're going to take a look at each one of those, do a very, very quick review of how to find the area. Note that all of these formulas for areas you will need to know. Okay? And a quick reference on the inside cover of your textbook, they're all right there. Okay, so if you just flip your book open, near the top of the right-hand page inside your book, you've got all the formulas at quick reference right there. You'll need to know all the formulas for quadrilaterals that we're going to summarize today. Well, first of all, start out with the easiest one. Rectangles and squares. As you know, we've done these types of problems and applications before. We're just covering it to make sure that anything that's on the screen you need to know the formula for. So we know that the area of a rectangle is, of course, just the length times its width. Square is actually not its own category of quadrilateral. It's a subcategory of the rectangles, right? It's just a rectangle where all four sides happen to be the same length. Okay, well, the next one we're going to take a look at is parallelogram. You might remember what exactly a parallelogram is by definition. All four sides, there's two sets of parallel sides. That is to say, both pairs of opposite sides are, in fact, parallel. Now, to find the area of a parallelogram, we still need to know the width of the parallelogram, or the bottom or base. The height or altitude is straight up from the bottom to the top. That is not necessarily what's called the slant height, or the dimension A of the unnecessary side. The dimension A shown up there is not a factor in determining the area of that parallelogram. So we just take the base times the height. Okay, parallelogram, both pairs of opposite sides parallel. Next one is a trapezoid. Anybody remember what a trapezoid is? And what is it? Stop there. That's right. One set of parallel lines. So, to find the area of a trapezoid, we need to find out what the average width is and multiply it by the height. Now, one way to think about that is just to take our two bases. The bases, B1 and B2, are the two parallel sides. So we add them together and divide by 2. That tells us the average width of our trapezoid. We take the average width and multiply it by the height. That tells us our area. B1 plus B2 divided by 2 times the height. Average width times the height. Where again, the height is the distance between the two parallel sides. Side lengths A and C up there do not factor into the area of the trapezoid. Now, one quick question. The one we saw previous to this parallelogram, could a parallelogram be considered one category of trapezoid, yes or no? Does a parallelogram meet the criteria of trapezoid? It does. Okay, a parallelogram does meet the criteria of trapezoid. It's a subcategory. It just so happens that it's a trapezoid where A and C, the two end sides, would also be parallel. Okay, and the last one is a rhombus. Anybody remember what a rhombus is? Rhombus is the coolest one, but it's also the most infrequently remembered. All four sides are equal length. And a rhombus doesn't have its own formula. It's just a special category of parallelogram. You can see a rhombus is like a square cardboard box that's collapsing. All four sides are the same. And we just use the parallelogram formula for area of a rhombus because that's what it is. Here we go. This room is about 16 by 28. We want to know how much it's going to cost to carpet the room. We're going to assume a couple of things. One, we're going to assume that, as is the norm, there's an extra allowance for waste. Because it's not a perfectly, they're not going to be exactly dimensions that are exactly the width of the rolled carpet. So we're going to allow 15% for waste. And we're going to round up. If we get a partial square yard, we're going to round up because we can't buy any partial square yards. And this carpeting is a high durability carpeting, and as a result is a little spendy, $37.50 per square yard. Now there's a couple of different things that we could do. One thing that we could do would be to convert our dimensions into yards to begin with. Okay? We'll just find our area in square feet and then convert our area into square yards, mostly just for a review on that conversion. So this room is 16 feet by 28 feet, which means our area is, now this is a rectangle, it's the easiest one to remember, so our area is going to be 16 feet by 28 feet. And that gives us an area of about 448 square feet. $448 square feet. Usually you don't buy carpet by the square foot, you buy it by the square yard, so let's do the conversion. 448 square feet. We can use 3 feet per yard, but we need to square that conversion since the units are squared. If we do that, we get 448 times 1 times 1, or 448, over 1 times 3, which is 9. And that gives us an area of about 49.78, leaving extra sig digs here, square yards. So our area is about 49.78 square yards. No trouble there? All right, well now let's allow that 15% extra for waste. So we're going to multiply this by 1.15. We need all this carpet plus an extra 15%. So we're going to take 49.78 square yards times 1.15 to allow 15% extra. That's going to give us about 57 point. For some reason didn't write down, I wrote 57.247. We'll call it 57.2 square yards, but ultimately it doesn't matter because we're going to assume that we have to round up. We can't buy a partial square yard, and so we actually are going to be buying 58 square yards. That's how much we're going to have to pay for. Well, then we're home free. It's $37.50 per square yard. That's basically a conversion fact where 1 square yard is $37.50. And we end up with a total cost of $2,175. Now, since our dimensions technically only gave 2 sig digs, we could argue that we'd need to round that off to 2,200, but dollars usually are carried out to the nearest dollar or penny, as the case may be, regardless of how many sig digs. So either way would be arguably correct, but we'll leave it at 2,175. How many bundles of shingles do you need to shingle this hip roof? Hip does not mean necessarily that it's just stylish. It's actually those of you who are in architecture know that's actually the technical term for the type of roof. A square of shingles, if you're not familiar, a square of shingles refers to 3 bundles. Basically, because when you lay 3 bundles of shingles next to each other, it forms a square, or one row on the pallet of shingles. And each square, that is 3 bundles, cover about 100 square feet. We want to know how many bundles we're going to have to need to shingle this roof. Well, you got 2 shapes going on here. What have you got? You got a triangle on the narrow end of the house, and you've got a trapezoid on the long end of the house. So let's start out with the triangles on the ends. The ends of the house are 24 feet wide. And from the edge of the roof, the edge of the roof, the lower edge up to the peak is 15 feet. So the area of each end will be 1/2 of 24 feet times 15 feet. 180 square feet per end. So that's how many square feet we've got on the narrow ends, Drew. Well, we're kind of drawing an assumption here. It's shown on the picture that it's 15 feet from the edge up to the peak. And most hip roofs have the same distance regardless of which edge you're on. Okay? Otherwise, you'd have a different number of rows of shingles on depending on which side you were looking at. So to keep it aesthetically attractive, they make it the same distance. Right. We'll factor in that there's 2 of them in a minute. Let's do the sides. We've got trapezoids with a height of 15. The bottom is 60 and the top is 36. Yep. So here our area is going to be 60 plus 36 divided by 2. Multiply that by the height. That is the slant height. It's the distance up that edge. And that works out to be, if memory serves, 720. Is that right? 720 square feet. So our total area two ends and 2 sides, so we're going to have 2 times 180 square feet plus 2 times 720 square feet. I think that gives us 1,800 square feet. So we've got to cover up 1,800 square feet of roof area. So just using your intuition, if the roof has 1,800 square feet, how many squares of shingles do we need? Nope. You need 18 squares, right? Each square covers 100 square feet, so each square would be each square covers 100 square feet, so we would need 18 squares, 3 bundles per square, so we'd need 3 bundles per square. 18 times 3, 54 bundles. Set it up as a conversion if you get a little bit mixed up there. 1,800 square feet. We know that there are 100 square feet per square. And we know that there is 1 square for 3 bundles. 1,800 times 3 divided by 100 gives us 54 bundles. Now here again, it would probably be a good idea to allow 5 to 10% for waste, because you're going to be cutting a lot of those shingles off. That'll vary on the type of shingle actually, but we'll leave it at that. 54 bundles is probably going to be a pretty good starting point. Okay, here's an interesting property that's not widely known, but it's just a little side note because we are dealing with figures beyond triangles now. Every triangle has how many degrees in it? And its interior angles total? 180. Did you know that all the other shapes, quadrilaterals, pentagons, hexagons, all have a similar rule for the total of the interior angles? It's just that it's not as widely known as triangles. This formula tells you what that sum is. Sum of the interior angles in any polygon with n sides is given by n minus 2 times 180. So for example, this need not be a square. How many sides have we got? 4. What's 4 minus 2? 2 times 180? 360. Every quadrilateral is going to have a total of 360 degrees on its inside. So in this case, we'd have 4 minus 2 times 180 degrees equals 360 degrees. Well, what if we had a hexagon? How many total degrees will there be? How many beers will there? We got 6 sides, so we're going to have the total of the angles inside a hexagon, 6 sides, is going to be 720 degrees. Now the question is, why does this work? Anybody know why it works? Why that formula is what it is? Once you see it, it's one of those, oh, of course moments. But does anybody have a little insight and see why it works out this way? Exactly. You can take any shape bigger than, or any polygon bigger than a triangle and break it up into triangles. A 4-sided figure will give you how many triangles? 2. 4 sides, 2 triangles. 2 triangles, each one has 180 degrees, 360. 6-sided figure you can fit in 4. You can always, however many sides you've got, you can always fit 2 fewer sides in, or 2 fewer triangles in there. So you subtract 2, and that's how many triangles you've got times 180 degrees. That gives you your total. Gabe? So with that in mind, let's find this angle theta. This is a regular pentagon. Regular means, what was that? Equal sides. Right. Equal sides, equal angles. Okay, all the sides are the same length, all the equals are congruent. Start with the pentagon. Okay? Start with the pentagon. Each one of the vertices in this pentagon will have how many degrees in it? Well, it's a pentagon, so let's take we're going to take 5 minus 2 times 180 degrees. We get 540 total degrees in the pentagon. Whoops, not 54, 540. That's the sum of those 5 interior angles. The question is, how many does each angle have? Now, if we didn't know that this was a regular pentagon, that all 5 vertices are the same, we can't answer it, because they could be divided up millions of different ways. But since they're all the same, what can we conclude each one of these angles is? Divided by 5 angles, we get 108 degrees per angle. So this one's 108 degrees. This one's 108 degrees. This one's 108 degrees. All right, well, that doesn't answer the question of how much theta is. We know that the whole thing would be 108 degrees, but we just want to find what theta is. Now, what do you know about this triangle down here? Since these two sides have to be equal, what kind of triangle is this? Isosceles, right? Isosceles triangle has two equal sides. So this bottom triangle is isosceles. What that means is that this shape is symmetric down the middle. This is symmetric down the middle, which means what has to be true about these two angles, theta and its mirror image over here? They have to be the same. So now look at your quadrilateral. How many degrees do there have to be on the interior of that quadrilateral? The quadrilateral's got to have, we already did this once, but 4 minus 2 times 180. 360 degrees. Well, we've got 360 degrees to give out to these four angles. We already know what that one is. So theta, these two together, that's got to equal what we have left after we use up 108 and 108 out of our 360. That's got to equal 2 theta. Does this give you 144? 144 degrees left over for both of those. So what's our angle? It's got to be 72 degrees. So we found it. 72 degrees. Two fundamental formulas about circles that you need to know and perhaps already do. The circumference of a circle, the distance all the way around. Circumference found is taken pi times the diameter. And of course the area is given by pi r squared. Now, maybe you're like me in that I knew these formulas at some point in my mathematical career, but it was a long time before I actually questioned where they came from. And the easiest explanation I've seen for where this comes from, you can just take a look at this. There's just a little explanation as to why. The question that I started to wonder after a number of time was, how is it? Isn't it a huge coincidence that pi, 3.1415926, is the same number used to find both the circumference and the area? If you think about that, that's kind of a coincidence, isn't it? Maybe not. Sort of a coincidence. Well, here's why it's the same value of pi. First of all, if you take a circle and cut it up into slices. Now, the one shown on your sheet and up here is cut up into 8 slices. But ideally, you would cut it up into millions of slices. Like an orange. If you cut an orange into slices and then slit it with a knife and peel it open. Okay, well, what would you get? You'd get that kind of toothed-looking thing there on the left. And you'd have millions of slices coming up out of it. Whoops. Well, what would the length of this thing be? What's the circumference of that circle? The circumference is pi times the diameter, right? Or in other words, pi times 2 times the radius. So the length of this thing is really just pi times 2 times the radius of the circle. That's how long this strip would be when we stretched it out. Now, assuming that you did this with millions of slices, would this thing even have bumps, or would it be pretty much flat? It would be virtually flat. If it was still bumpy, you didn't cut it up into enough slices. Cut it up more. Then you take half of it, snip it off, and take these pieces and slip them into those. And you get that picture on the bottom. You'd end up with basically what would be roughly a rectangle where these pieces fit together. Now, this thing was pi times 2r wide. How wide is it now? Pi r. Half that. And how tall is it? How tall were these slices? The radius of the circle. So you get basically a rectangle. And what's the area of that rectangle? Pi r times r, pi r squared. That's where the formula for area of a circle comes from. It's actually derived from the formula for circumference of a circle. And the circumference, of course, is just how many times the diameter will wrap around the outside edge, 3.1415926. Really kill it. Circumference of that circle is 48.00 inches. Find the area of that shaded area, the blue one. We will always use the pi button on your calculator because if you use 3.14, you're always limiting yourself to 3 sig digs in everything you do. If you use the pi button on your calculator, you've got like 12 sig digs. Pi will never be a factor in your answer. Pi will not typically limit your sig digs. So pi times diameter, which means our diameter is going to be 48.00 inches divided by pi. And our diameter works out to about, I have 15.279. How does that look? We were originally given 4 sig digs. We're going to leave a few extra. I'm going to leave 5 here while we do our work. We'll round off at the end. 15.279 inches. Okay? Well, that's all fine and dandy. We got the diameter of the circle. That's 15.279. Now, what can you find based on the fact that the diameter of that circle is 15.279 inches? Find the area of the square, because to find the shaded region, you're going to take the area of the square and subtract the area of the circle. So the square square's area is going to be 15.279 squared. Which works out to be around, again, leaving a few extra sig digs, 233.45. Circles area. Well, find the area of the circle. We're going to take pi times the radius squared. We need to go back to the diameter and divide it by 2 to get the radius. 15.279 divided by 2 gives us a radius of, didn't write it down, 7.6295 inches. So our circle's area is going to be 6395, thank you. $7.6395 squared times pi. That gives us the circular area of 183.35 squared. Anybody want to verify that? Is that right? 183.35, okay. Well, then our shaded region $233.45 minus 183.35 gives us an area of about 50.10 square inches. We started with 4 sig digs. We've got 4 sig digs. When we're done, we'll call it good. 50.10 square inches is the area of the shaded portion. All right, a little bit of terminology now. We got just a couple more examples pertaining to circles, but a couple more terms. Again, I apologize that your copies don't have this brilliant color display. Tangent line is any line that just brushes along the edge of a circle. We would say that that red line is tangent to the circle. When a car sits on the road, the surface of the road is tangent to the wheel. That is to say, it just contacts it on the outside. Now, one property about tangent lines that's not earth-shattering but worth knowing is if you have, for example, a wheel is the best example of this. If you have a tangent line to a circle, what do you suppose you can always say about the tangent line and the radius that contacts that tangent line? There's always one radial line that will contact that. What do you suppose has always got to be true about these two lines? 90-degree angle. That's right. That is to say the center of your wheel is always directly above the point of contact. Makes sense, but it's worth noting that a tangent line is always 90 degrees to the radius, the radial line at the point where it contacts. A couple other of terms. A secant line is if a tangent line gets too close and slips inside, contacts the circle twice, you have what's called a secant line. A chord is the lined segment, part of a secant, where the endpoints are on the circle itself. A secant extends out beyond the circle. A chord is contained within the circle and just has its endpoints on the circle. Okay. Well, here's an example related to tangent lines. We've got a circle, and from some point off the circle, we got some point off the circle, and the distance from the center of the circle to that point off the circle is 0.925 inches. That point is on a tangent line that's 0.850 inches from the point of tangency where it contacts. We want to find the circumference of the circle. I'm going to change the way this is drawn just slightly. Well, you want to find the circumference of the circle, which means you need to know the radius, so you can find the diameter, multiply it by pi. Well, you probably see it. How are you going to find that radius? That's an equilateral triangle. Excuse me, it's not an equilateral triangle at all. It's a right triangle. And so we can use the Pythagorean theorem. We know that 0.850 squared plus our radius squared is going to equal 0.925 squared. To save time, we won't go through all the solving of that. I think you've all got Pythagorean theorem down without too much trouble, but the radius turns out to be, did anybody get it? 0.36, we'll leave, we got 3 signigs going in, we'll leave a few extras, 0.3649. Good. Okay, so if our radius is 0.3649, then our diameter is going to be, multiply that by 2, 0.2798. That's not right, what the heck? Diameter is smaller than the radius. 0.7, oh, thank you, 7298, thank you. I did it in my notes too, 0.7298, is that right? Yeah, okay, good. So our diameter is 0.7298. Well, then we're set. The circumference suddenly I have very little faith in my answer. What did you have here? 2.29, 3 sig digs in, we'll report our answer with 3 sig digs. 2.29. We found the circumference of the circle. A sector is like when you cut a slice of pizza, what you're doing, even though you don't know it, maybe you refer to it as a sector, but a slice of pizza is in the shape of a sector. So I dare you to go to the cafeteria now, get your lunch, and ask for pizza by the sector. An arc is just the crust. Okay, an arc length is a distance that's a portion of the length of the circle. We're going to do a lot with arcs and sectors a little bit later. And the segment is the little portion that gets clipped off by a chord and an arc together. Well, let's do another quick example here. We've got a circle here, The circle's got a diameter of 20 inches, and that chord that's shown is 12 inches long. We want to find out what the length of x is. Well, here's a fact that's listed in your book. Your book gives a lot of properties of circles, chords, and whatnot. But one fact about a chord is, if a chord meets a radius at 90 degrees, then it cuts that chord in half. It cuts it in equal pieces. You can't have a radius that cuts a chord in half and not meet it at a 90-degree angle. And the reverse is also true. If a radius cuts a chord in half, you know that it must form a 90-degree angle. So if a chord and a radius meet, if it's a 90-degree angle, it must be cut in half, and if it's cut in half, it must be a 90-degree angle. So based on that, we know that this chord is 12 inches long, which means what is this length? That's got to be 6 inches. Now we want to find x. We don't have a formula for finding x, but if we knew this distance, we could subtract it from 10 inches. How can we find that distance? We got a triangle here. Do we know the length of the hypotenuse in that triangle? Sure we do. It's the radius. The diameter of this circle was 20 inches, so r is 10 inches. So this is 10 inches. Let's call this distance over here b. So we know that b squared plus 6 squared equals 10 squared. Solving that, you'll find that b equals 8 inches. Well, if we know that b is 8 inches, how much of this radius is left down here in portion x? X is going to equal 10.0 inches, our radius, minus the length of b, which we know to be 10 inches minus 2.0 inches. Turns out to be 2.0. 3 sigdigs in, we should have 3 sigdigs out. These all work to be exact. We didn't have any rounding, so we'll report it 2.00 inches. Okay. Does that look all right? Okay, the last one we don't have time to solve, but let's just point out the feature. The area of that gray region, we would want to find it. Well, could you find the area of that semicircle? You know the diameter of the circle, and so you could find out what the area of the whole circle was divided by 2, you'd have the whole semicircle. Can you find the area of that triangle? Shake your head, yes. How can you find the area of that triangle? Here's an interesting property of semicircles. No matter what, no matter how hard you try, no matter what you do, if you form a triangle such that the hypotenuse is on this flat edge of the semicircle, no matter where you put the other vertex of that triangle, whether it be here or here or here, no matter what, when you fill in your triangle, you will always have a 90-degree angle. You will always have a right angle. Therefore, we know this side, 7.50 inches. We know this side was 6.25 inches. What are you going to use to find that side? Pythagorean theorem. I'm just going to tell you so you can mark it down on your chart that the length of that side when you use the Pythagorean theorem is 4.146. The area of the circle, if you do the math, the area of the semicircle, we'll call it SC. Area of the semicircle turns out to be 22.09 inches squared. Area of the triangle, 1/2 of 4.146 times 6.25. It turns out to be 12.96. Subtract this from that, we get the area of the shaded region, which turns out to be 9.13 square inches. Okay?